The issue of plate tectonics and how it relates to climate, potential regulation of climate, and life is one that's led to discussions that have filtered their way well outside of meeting rooms like this. And the way to convince yourself of that is to run a keyword search. You can do this as I did before I came to this meeting. I just plugged in life and plate tectonics, and you will get 2 million plus hits. Since I'm told we have extra time, I guess we can go through the 2 million? No. We're not going to go through the 2 million, but if you do pull them up, do have a look just to convince yourself that the little highlights I've pulled out in blue aren't us just cherry picking in any way. That is the dominant view you will find. That's the one that is expressed. Now, Google notwithstanding, we did want to be a little bit more precise about this. Scientists like precision. And at some sense, we also wanted to maybe question the prevalent idea, push on it a little bit. It might push back, it might be correct. But in terms of the precision aspect, the ideas that plate tectonics relates to life, they're not tied to the laws of plate tectonics themselves. That is, the rules that exist for plate tectonics and the quantitative laws for motions of rigid objects on a sphere. One of the beauties of plate tectonics itself as a theory is that it is precise. It does make some rules, and that has been very helpful. The connection to life isn't tied to these testable aspects of plate tectonics as a theory. What it's really more tied to is the idea of volatile cycling, and there's a little cartoon here that's a classic cartoon now. And in particular, and this is the aspect we'll look at, the volatile cycling as it relates to climate buffering. That is CO2 from the interior of the Earth coming out as a greenhouse gas into the atmosphere, and also plate tectonics creating new weatherable surfaces through mountains, through volcanism, that can actually act to draw down the CO2 from the atmosphere, and that might allow for a buffering. Now, plate tectonics is certainly something that allows for that, but what we wondered about, is it possible that there are other tectonic modes that allow for volatile cycling that can stabilize or buffer climate? And that's the question we principally wanted to address. There are many things that make our planet, that make the Earth the Earth. Here's a few of them. They're selective. We've tried to be careful not to use the phrase stable climate. That can be a little bit misleading. And instead, we've gone with stabilized climate, because stability itself, if we want to talk about stability, in particular in terms of the climate record, is a relative term, and we need to think about time scales, and we need to think about deviations from the time scales. Most certainly what stabilized climate means in this case is not a constant. The Earth's climate hasn't been constant. It's gone through fluctuations. Here are some climate proxies. And through those fluctuations, life has been fine. So we don't want to, and it seems it would be unfair to demand more of a planet without plate tectonics. And this is what we mean by stabilized. No runaways, as Diana said, potentially to a greenhouse state. No runaways to a state in which liquid water cannot exist. And we'll still go with that as a principal criteria. Again, plate tectonics comes into this story through its ability to cycle volatiles from the interior, maybe I should say from the downstairs to the surface and the upstairs, and potentially cause a regulation. So that's the springboard. Is this the only thing that allows for that, in particular with the starting point of a stabilized or buffered climate? What else can we consider? These are numerical experiments of convection in the rocky interior of terrestrial planets, with also the surface expression of how that convection manifests itself at the surface. Plate tectonics at the top is characterized by the continuous, relatively smooth overturn of the cold upper boundary layer, what we call the plates, sinking into the interior, cooling the interior, and you can see that on the slices of temperature. The red is hot, the green are colder. Also, in terms of the surface expression, what's being shown at that one snapshot, the yellow regions are regions of relative weakness, narrow plate boundaries that form within this experiment that allow the otherwise strong and cold plates, the gray, to overturn and participate in mantle convection and cool the interior. The other extreme end member on the bottom is a single plate planet. And if you look, there are no plate boundary zones. And if you have no plate boundary zones, you have no plates in the plural. You have a single plate that is so strong that it cannot deform and participate in interior cooling. Then you might have volcanism, tractions, different things that deform the surface. The speaker after us, who I'm glad to hear is still here, because that is what I anticipated, is going to specifically talk about how volatile cycling might work on that type of planet. So I'm not going to say too much more about it, other than I look forward to hearing what Lindy has to say about it. There she is. I am now comforted. There's your setup. We're going to focus in on this intermediate mode, an episodic regime. That's been noted by many people. We're certainly not the first. It's characterized by periods where the surface doesn't deform, it's in a stagnant lid state, and then periods where the upper boundary layer go unstable, overturn, and sink into the interior. And the surface expression looks different than plate tectonics. So that's the one we want to focus in on. Now, the motivation from some of my co-authors and myself goes beyond just other planets. It's been suggested that this mode of tectonics operated on our own planet in the Precambrian, the early Earth. The evidence used to make that argument comes from several data sets, some older than this one, but I'm actually just showing the particular one that's a paleomag studies of ancient continental sections, seeing how they moved relative to the magnetic pole of the Earth. That's an apparent polar wander path. One interpretation of this, and there's consistent results between two groups, which is nice to see, I was only involved in the first one, is that these lulls in the apparent polar wander do actually represent periods of time when the surface was not in motion, when you might have had something akin to a stagnant lid state, and then the bursts in velocity do represent the overturn and the episodic motion in the ancient continents moving. The simulation below shows how this would actually also affect heat flux coming from the core, which might affect the magnetic field and also the surface heat flux. Those are interesting things. Ask me questions about them. What we wanted to focus in on was the climate signal. And Diana set up this in some aspect very nicely for me, that one of the first things we want to think about is melt production. How much melt is produced, that ties into how much CO2 might get out into the atmosphere, water, if you're interested in that as well. And here are some results from calculations in an episodic mode and in a plate tectonic mode. And you'll see that certainly the pace at which melt is produced is clearly different. So we can actually use those and think about how that might affect a climatic signal. Here's the result, and I'm going to give you the result first, and then we'll walk through as to how I got it. This is the climate response of an episodic mode. Again, you see the Earth's climate signal from the time we have paleoproxies. On the right is the result from a coupled interior and surface processes model, and it's showing variations about the average mean surface temperature relative to an assumed reference state. That's the zero. So how did we come up with this model? How did we get it? So we have to link the internal dynamics, and that comes from these convection calculations, which actually give us production rates of melt. We have to make some assumptions, and Diana talked a little bit about this as well, how much melt actually makes it to the surface, so that's a parameter we can vary and see how it responds. And we can actually put those results into a model that will look at the climate response. We also allow for some variations in the nature of the episodic behavior. That is, what you're looking at are the results of two different models, and these variations come from changes in the parameters that go into the models. In this case, in particular, the internal viscosity structure of the planet can have an effect. For the Earth, we have constraints on that viscosity. We don't know it perfectly, so we do vary the models between the ranges that we think are allowable to see how that actually affects the periodicity times, the amount of volcanism produced. For planets and other solar systems, this will become even more important to do that and cover the full range. So we cover some range. That can be used to couple into a climate and surface process model. Now, for those of you who might be in the know about this literature, this springs from and builds upon the earliest studies from Walker et al. in the 80s, and carried on by Berner and then on into geocarb. Now, we don't do things exactly the same. There are assumptions that go into the models. But for this talk, which has a comparative aspect, what I'll say is what we do is not drastically different from the models that were used to actually look at climate stabilization with plate tectonics. So we could try to do an apples-to-apples comparison as we actually vary the tectonic mode to episodic. So what we need to know is something about the carbon in the ocean atmosphere system, the volcanic outgassing. We get that from the models we are running. In our case, there's no tidal heating, just an Earth-like state, internal temperature driven by decay of radiogenics and primordial heat. We also have to deal with weathering. In this case, we're just doing basalt. We're not going to worry about granitic continents and just assume basaltic volcanism. We have predictions about the resurfacing rate, so how much fresh area is put on by the episodic mode. We can actually make some predictions about topography to get some idea of mountains for our mechanical weathering function. And we always do assume, and this is critical, that the planets we're thinking about have an ocean, but always some area of land above that ocean to allow for drawdown and to allow for the buffering, and that is critical. And then that goes into a climate model, a 1D radiative convective atmospheric model, and we make the predictions about the temperature over time. The forcings, there's the periodic resurfacing, the forcings that come from the interior, the episodic variations in the tectonic mode. We're assuming, for all the cases I'll show you here, that we do have a wet mantle, that there is water in the mantle, a wet mantle solidus, and we do track water cycling. In the interest of time, I'm focusing on the CO2, but if you're interested in the water cycling, please ask. We create topography, have it weather according to the weathering functions, and then we track changes in resurfacing area for the weathering, principally volcanism for the volcanic activity. Responses, the critical ones for what we're talking about here today, partial CO2 pressure in the atmosphere, and how that relates to surface temperature changes for different variations in that episodic mode. And I'll let you take that in. And that's the essence of the model, and we can run through various parameter space models, various variations. The main conclusion here, and I'm at actually one of my main conclusions, and actually the main conclusion, is that you'll see that the fluctuations are not too radically different from those on the Earth, which is to say that in this mode, in this episodic mode, climate can still be buffered. There are potentials for runaway scenarios here, but there are a significant number of cases within parameter space that do allow for a buffering. And there's a conclusion. I didn't know I would have extra time, so I thought actually people would appreciate one clean conclusion in a 15-minute talk after 5 days of 25,000 people talking at each other. I hope you still appreciate that. This is the hard one conclusion we have. Now, I guess I do have extra time, so I can spring a little bit. Okay, I get the nod into some of these other issues. The other issue here is that maintaining a climate that allows liquid water at the surface might allow things to live there, but you'll notice I've been sly. I haven't talked anything about what kind of things I'm thinking about. Not all habitable planets are the same. Habitable by what? If you were now to ask me, Adrian, is plate tectonics required for a planet to have life in general? I would say myself and my co-authors might be leaning a little bit toward the no side. If you were to ask me, is it required for planets to have what we might call higher life? I would first tell you that nothing that I've said up until now actually relates to that in any direct way. It doesn't. We've actually started to think a little bit more about this, and our thinking is that for higher life, plate tectonics might indeed be important. Let me just show you a few of the preliminary results from that, and they are preliminary. So this is the work from Vlada principally. And what Vlada was looking at was another upstairs-downstairs cycle, if you like, and one that I think will still be talked about today, even though Lee can't make it, oxygen. And the upshot here from the models he's done is that it's difficult to allow for a buildup of oxygen in the atmosphere, certainly in a stagnant lid model, that plate tectonics might tie into this more critically. And it comes through feedbacks between the effects of oxygen on rocks, similar to the effects water has on rocks in terms of affecting melting properties, in terms of affecting strength. And this feedback in a plate tectonic mode allows for oxygen to build up in the atmosphere. That might be difficult under other circumstances. And if oxygen is critical to higher life forms, then this is suggesting that indeed this tectonic mode might be critical. And that's interesting from our perspective too. You notice we started thinking about plate tectonics not being critical, but now we're focusing in on different types of life. The other thing that's got us thinking about this is one that I originally started thinking about with Craig O'Neill, and it goes back to what I noted about this idea that the Earth might have transitioned in tectonic states over time. And that's nice for planetary scientists because in a way the early Earth becomes an alien planet, a different planet. That it might have gone through an episodic mode, and indeed, I think Lindy will talk about this, there are arguments that perhaps the early Earth itself was stagnant. There's the paleomag evidence. There's other evidence that have been used by various groups to argue for this, that modern-style plate tectonics didn't initiate till about 1 billion years ago. If we look at that and we say perhaps that's viable, we can do something that I will freely admit is speculative, and I hope it's provocative. Just put dated events in the tree of life below it. And I know correlation is not causation, but there you go. It does suggest something to us anyway. I don't want to end too speculatively, so I'll come back to the conclusions. And actually, I'm going to thank you for listening now. If there are some questions, I have other things we can come to. But thanks for your time. Oh, well.
Yeah, please use the microphones.
So the question I would have is really around episodicity versus actual plate tectonics. To draw that distinction, is it around the the problems you have with higher life in episodic or stagnant lid cases because they are potentially catastrophic or because they're not communicating with the interior, or is there something about plate tectonics and one-sided subduction and all those sorts of things which you think is important for the emergence of Carl Sagan?
Yeah, fair enough. The emergence of Carl Sagan. So far, and I should clarify, the models Vlada has done have not looked specifically at the episodic mode in oxygen. It was actually looking at the difficulty in the stagnant lid mode and oxygen. And actually, Vlada's right in front of you. If you want to, is it okay if he just answers? Yeah. I mean, we're kind of freewheeling, right?
The major thing is really the pace. That's the major problem. So it's really the pace question, which I think Adrian was mentioning very much, and I think that's where it goes to. And the major thing we try to do with this whole thing is, just to be clear about what we're actually really claiming when we talk about plate tectonics in life. And I think the general argument, and that's where we're getting more and more consistent, that what we believe based on the carbon cycling and climate feedback, that's, I think, not really maybe the right thing to think of. But when we go then for oxygen formation, and there you will have a problem to, you need a high pace of contacting the surface with the interior to be able to regulate that. And even episodicity then might be problematic because you can build up and then you have a strong overturn and you subduct everything down. So it's very, very unstable. And that's the good thing about plate tectonics in that case.